Alrighty, so we're going to continue our discussion of factorial experiments. So what we first do is, like a factor, like in the example I was using, like temperature and music, there's many levels of temperature and there's many levels of music, but one of the things we do is we just restrict it to a high level and a low level to see if that factor has any effect. So we're not necessarily mapping it out exactly, but we're trying to screen through a large number of factors and say which ones are actually relevant to my problem. So we're going to set two levels, and we will draw this out, and we would say that factor A and factor B will have a level here, combo here, here, and here, right? Which creates a nice little box. And we have this interesting property called sparsity of effects. And it's this general principle. It doesn't happen all the time, but it happens in enough cases where we kind of use it to get some traction, and you know, it's some risk, but we use it to get traction on our problems. And the sparsity of the effect says if a main effect, that would be like A or B, I'll abbreviate ME. If a main effect is not significant, then an interaction with the main effect is not significant. Now, it's important for me to stress that this is a not steadfast rule. It's not a law. It doesn't happen all the time. It just is that we find in practice that in, maybe I should say most experiments, that if there's an interaction effect between two variables, then one of them is going to be significant. Okay. Now it could be like the circuit breaker, the dimmer switch, right? The dimmer switch is significant, right? It makes it go bright light. The circuit breaker is significant. If the dimmer switch is at the brightest setting and you turn the circuit breaker off, the light goes out. You turn the circuit breaker back on, the light goes on. So it is significant, both of those factors. And then there's the interaction effect. It could be, however, that when you have the setting of the dimmer switch low, right, you don't observe an impact from the dimmer switch because the circuit breaker's off, or you don't appreciate the circuit breaker because the dimmer switch was set to low, right? So it could be something like that. But generally, if we set low and high values and we've properly covered the span of the space, and it's not like some sort of weird pattern that gets high and then low and you just missed it, then if one of those factors is not significant, then that factor is probably not included in an interaction effect in general. Doesn't mean you'll have covered it. So what we had described before is the way I'm going to estimate factor A is I'm going to take the average of when A is positive minus the average when A is negative. And I want to estimate B. I'm going to take the average when B is positive minus the average when B is negative. And if I want to do the interaction effect of AB, I will do the average of when A times B is positive minus the average of when AB is negative, right? Is how I'm going to estimate those factors. So let me make a table. If I have three factors and the two levels, then what I can do is write out my factors A, B, C, okay? And I can look at all the combinations. So I'm going to have a negative, positive, negative, positive. Wait a minute, how many am I going to have? Well, three factors, two levels, that is 2 to the third, or 8 experiments. So I'm halfway there. Minus, positive, minus, positive. So now for B, I can go minus, minus, plus, plus, minus, minus, plus, plus. And then for C, I can do minus, 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 minus. And hopefully you see the pattern because it allows you to very quickly map out all of the combinations that you might have between A, B, and C, right? And we would call this experimental order. So if I put an experimental order here, I would have 1, 2, 3, all the way down to 8. Okay? Now, if I'm going to take a factor AB, right, which is the interaction effect between A and B, then the way I would calculate what that level is, right, from this type of equation, well, I just multiply the two. So a negative and a negative is a positive and a negative is a negative and a positive is a negative, positive and a positive is a positive, and so then we would do the same pattern here, would be positive, negative, negative, positive. Okay? What I would like you to do is I would like you to calculate the interaction for BC. So just pause the video for a minute and go through and calculate the BC interactions. All right, I'm assuming you've paused the video and now you're returning. So if we do BC, we have a negative and a negative is a positive, negative and a negative is a positive. That's a negative, 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 positive, positive. Okay? Now you'll notice that it's different. So when I want to calculate the values for, now I've done eight experiments where these factors are all laid out differently, right? These are the factors that I am varying, right? So I've done these combinations. Well, what I'm going to do is I'm going to select run 1, 4, 5, and 8 at the high level. I'm going to average those values. I'm going to take the other ones, I'm going to average those values, I'm going to take the difference, and that's how I'm going to get my AB interaction. When I want to calculate the BC interaction, I'm going to take 1, 2, 7, and 8. I'm going to average those data points together, and I'm going to subtract the ones from all the experiments in the middle, and I'm going to take the difference there, and that's how I'm going to calculate the BC interaction. Well, what happens if I say when does AB equal C? Where does AB equal C? This is called confounding an interaction effect with a main effect. And so if I find where A, B, and C are equal, are they equal here? No. Are they equal here? Yes. So that would mean that this experiment is one that they have the same, and same with this one here. So I'll take these two. And then C is equal to a positive here. They're the same. Did I do something wrong? Yeah, here's a positive. And then the other one is here. So that's 2, 3, 5, 6, 7, and 8. 5 and 8. So if I run these experiments, right, 2, 3, 5, and 8, and only those 4, well, I will be unable to determine whether I've observed a difference in C. Because look at this. The numbers that I would run here, right, would be for estimating a factor C, right, what are the values at the high? The values at the high, right, are going to be from experiment, I'm only running a subset, so I don't have 5, 6, 7, and 8. I only have 5 and 8 minus from experiments 2 and 3. But if I have AB, what is that? AB is, also 5, 8 minus 2 and 3. So the estimate for AB and the estimate for C is going to be exactly the same number because I've only done half the experiment, right? Like if I did these other ones, right, like where this is a high value, experiment 4, and this is a high value, experiment 1, but C is negative, right? So now the equations are going to be different if I have all of the data points. But with this subset that I've chosen, C and AB are exactly the same. Why would I do that? Well, sparsity of effects. If I run this experiment and I find that A is not significant and B is not significant, then I would conclude that if neither of these are significant, then the A-B interaction is probably not significant either, and then I can conclude that C is the significant factor and I can be done with my experiments. If, however, I find multiple factors are significant, well then guess what? I can just go and run the other four, the other half of the fraction. And then I can figure out now is A, B, C, or what interactions are significant. But if I get lucky and I find that A and B are not significant, C is the only factor that is, then I've run half the experiments and then I'm fine. Okay. So that is how we do a fractional experiment. How do we do the analysis of it? Well, essentially what I would tell you to do is design your experiment like I'm showing you here. Design your experiment. Try and control the noise variables to the best of your ability. Kind of try and control the other variables so that they don't kind of interfere or create some crazy effects. And then you design your experiment, then use regression. Well, what is regression? Well, regression essentially is if I have X and Y and I have a whole bunch of data points here, right? What I'm doing is I am going to do my best to fit a line to them that follows this equation, y equals some intercept, right, plus some error. And then what I'm essentially doing is I'm doing a test, a t-statistic on beta 1 divided by the standard error of beta 1, which is basically testing this hypothesis that the beta 1 equals 0, meaning that what happens when beta 1 equals 0? Well, if it equals 0, the slope would be flat. What does it mean to have a flat slope? It means that as you change x, there's no impact in y. So if this p-value is very, very small, right, out here, and I get a very, very small value for my p, then what that's telling me is this hypothesis cannot be accurate and there actually must be a relationship between x and y. That's what tells me that a particular factor is significant. Okay. The other measure that is of relevance is called the coefficient of determination, and it is r squared, which equals 1 minus the sum of squared error over the sum of squared total. And the sum of squared error comes from the variance of this guy right here, right? That's how much error is done after we explain with a line. So if you look at this data point, there's a value that's really, really high here, and there's a value that's very, very low here. So all of these data points, right, occur at different values, right, on the y-axis, and so there's a large variance here in y. That's the sum of squares total. Well, once I put a line to it, right, now the distance off the line is much smaller, right, than it was before, right? And so that smaller variance is the sum of squared errors. After you have a line to explain why this point is high and this point is low, right, there's still some variance. That's what goes in the sum of squared errors. So if this is much, much smaller than this, then your r squared is 1. If they're about the same, then this becomes 1 and this goes to 0. It's not ever possible for the sum of squared errors to be smaller or to be bigger than sum of squared total. If you had a line that was completely flat for your model and you didn't even try to explain it, well then the deviation from the mean, right, keep in mind that the variance equation is the sum of y minus y bar squared. So that y bar is the line that's the mean right there. So if you have no model at all, right, if you have the worst possible model of just, hey, I think it's the mean, no guess whatsoever, then this error would be the same as sum of squared total. So this r squared number is going to go from 0 to 1, and it's going to tell you how well your model has explained the data that you've collected. Okay? Any additional factor you put in there, R-squared can only get better. It can never get worse, right? But it doesn't tell you that it doesn't tell you whether or not you have explained the data well, right? So you can have a case that I often like to use with like grades. So I would give people their exam, and it used to be I was in a university where I could see how many homework problems they did, and then does that predict their score on the exam? And so I would always find that it was about 20% R-squared, but the slope was highly significant. Why? Well, it's significant because if you do more homework, you will do better on the exam, right? That's just the way it works. But it's but one factor. So other things that impact your ability to do well on exam might be like your SAT score, how well you did in the previous material, how much sleep you got the night before. There's a lot of other variables that go into that. And so we use R-squared as a way to say, have we put enough data in there to really explain it? Or if I add this extra factor in there, does it really boost the R-squared? It might still be significant, but does it really help me model and understand the data and do something with this model at the other end? Okay. One other point that I want to come back to is this idea of center points, right? So if you have like a lot of extra experiments that you're wanting to run, right? How do you know how much variance there is in the data in general? Well, if I were to put an extra data point, let's say here, right? If I was going to put an extra data point here, well, that doesn't really like make me feel comfortable because now I've got like 2 data points here and I've only got 1 elsewhere. So I've now created some sort of leverage on my design, which I don't like. But if I put a point here in the center, right, it's neither high or low, so I don't have to really use it to estimate factors. But if I put a bunch of extra points here, 3 or 4, I can estimate the overall variance and I can get a better estimate of the error that I have in here, and then that can help me, that factors in when I do the regression to get a better estimate of the distribution so I can be more confident when I see one of these factors. So we don't really want to do this. We want to get rid of those, right? What we want to do is we want to put additional points here, and we call these center points.